Good afternoon. I would like to welcome you at webinar, which is related to machine learning prototype for space applications. And the agenda of the meeting today is the objective of this webinar is to present the prototype of a machine learning tool to enable the exploration, analysis, and interpretation of the outputs of large volume cosmological simulations using representation learning techniques. The tool efficiently learns a low-dimensional representation of the structure of simulated galaxies in arbitrary physical components, uncovering their intrinsic structural distribution. It also provides an interactive hierarchical visualization of the entire simulation and its compact representation, and scales to arbitrarily large simulations beyond the exascale era. And today, the tutorial will be delivered by Sebastián Trujillo Gomez and Bernd Dozer. They are both part of the space project, and they created this tool for you. So please, Bernd, Sebastián, you can take over and start your presentation.
So first, I want to thank Marisa and also all the organizers of this event. Today I'm here to tell you about the work that we've been doing on developing machine learning tools to help researchers make discoveries, power discoveries from their simulations. But some of you may not be working on simulations, I understand. So I want you to think of this more generally as large and complex data sets. The idea here, we're starting with applying it to simulations, but they can be, these tools can be generalized to be applied to any kind of large data sets that are difficult to explore and analyze. We're using, like I said, cosmological simulations as the first test case. This is my field of expertise. So I'll tell you a little bit about what these kind of simulations do. To understand in general what simulations are good for, we can use this quote from Richard Feynman, who said that in order to understand something, you need to be able to recreate it. So what cosmological simulations do is they attempt to build a universe inside a computer using the known laws of physics. And of course, you need the model, or the Big Bang model of the universe, which gives us very precise initial conditions right after the Big Bang. We start at that point, and then using the known laws of physics, we evolve this universe in a box until the present day for 14 billion years. And we watch the development of all these structures that we see in the sky, stars and galaxies, and so on. And the goal is that by reproducing all these processes in a computer, we can better understand how where these objects come from. There's a long history to this field. And almost 30 years ago, when we already had all the elements in place and some supercomputers and the codes to do this, people realized that an incredibly large amount of physical recipes have to be included in order to understand how galaxies form. Galaxies are the main objects that we want to study in these types of simulations. This is where most of the action happens in the universe. We live in a galaxy ourselves. And here you can see on the right just a short list of some of the ingredients that you need to understand in order to put the physics into the simulation. So not just gravity, but a lot of other fields of physics are involved. So this is an extremely ambitious and difficult challenge, but this is also what makes it so interesting. And this is what I've been working on for most of my career as an astrophysicist. So let's say that you can assemble all these ingredients together. You write your code, you go to your favorite supercomputer, you get a lot of computer time, and then you have to wait about 2 years for one of these simulations to finish running, one of these state-of-the-art simulations. And you have to spend about 100 million CPU hours. So it's a big amount of time that you have to spend on this. So you're hoping that your simulation did not produce corrupted results. But at the end, you can visualize it this way. This is sort of a general overview of what the simulation volume looks like. It's a cube that it's a representative volume of the universe. You can see on the left the emergence over time of this cosmic web due to the gravitational collapse of the material in the large scale universe. And on the right, you can see that the gas, the stuff that eventually ends up making the Earth and us and everything we know is actually following this cosmic web. But there's a lot of more stuff, including all these fireworks happening in this view, because the gas has much more physics than the dark matter. And so, and this implies that all these scales are coupled together. And this is what makes the simulation so challenging to run and also to understand. If I was to show you here where the galaxies are, you would not be very impressed because they would only take about a couple of pixels each. Galaxies are extremely tiny compared to the large scale universe. So the objects that we're interested in forming, we really have to zoom in a lot to see them in the simulation. So this is why the simulations have this multi-scale challenge. You can see here, you begin to zoom from the scale of the simulation itself by about a factor of 10 to begin to see the filaments in the cosmic web, and on another factor of 10 to see the largest structures in the universe, and then another factor of about 100 to begin to focus on a single galaxy and its internal structure. And so this internal structure here is what we're focused on. But in order to get this galaxy to form, we have to form the entire universe in a computer. And this is part of what makes this kind of work so challenging. So you might wonder if all the information is in a simulation, all the details of this formation of each of the objects in the simulation is there. Why is it so difficult to interpret them? So the answer to this is that the data is very complex and the data set is very large. And you can see that exemplified here. This is one galaxy out of about a million galaxies in this single data set. And now we're following it in a zoom version of just its neighborhood over time since the Big Bang until now. And you can see that the formation process, how it accretes gas from its surroundings and how it expels gas to black holes and stars, dumping energy back into the galaxy. This is very messy, and there's stuff flying around everywhere. The dynamics are very complex. They're very difficult to describe with a simple recipe. And this is all happening in 3D, and it all depends on the sort of large scale environment that you can see here in this box on the lower left. And this is intrinsically a 3D process. You can see that when you turn the box around in this view. So it would be very difficult to describe it just in a two-dimensional image as we're looking at here. You can also, it's intrinsically multi-dimensional, this data set, because the matter can be visualized in many different physical attributes. As you can see here, you can look at the chemical enrichment of the gas, you can look at the temperature of the gas, its velocity, you can look at the brightness of the emission, lines and from different elements. So all in all, you end up with more than 100 different dimensions of the same data in this one galaxy out of a million in this data set. So when I describe this, I want you to think about your own data. Perhaps you have something that is equally difficult to understand. So if you can think of something like this, then you can use our tools to better understand and get scientific insights from your data. And this is the goal of the seminar. So this means that we have this data problem, in particular with these kind of simulations, the largest projects that require petascale HPC computing evolve a universe in a box with more than 1 million objects, which are the galaxies in this case, about 100 billion resolution elements, and this is continuing to grow, and they live in 100 or plus dimensional feature space, generating about a petabyte of data per project. And for exascale simulations in the next decade or so, these data sets are going to grow to be more than 100 times larger. And this is a review as of last year of the progress of the state of the art in these simulations in terms of the size of the box that is simulated. This is already hitting on the size of the observable universe, and this is the mass of the resolution element. But these lines here show you how many resolution elements or particles you have in each of these simulations. So now we're scratching about 100 billion resolution elements. But in the exascale era, we're going to reach to about 10 trillion, presumably, with data sets that, like I said, are about 100 or more times larger. So this is really going to be a huge challenge to run the simulations, and this is what we're working on also in the space project, but also to analyze them, to analyze their outputs and to store them and to provide access. So here's an example of what this data looks like. You have the raw snapshots from the simulation containing basically a list of all the resolution elements, and you have about 100 or so snapshots in time describing the time evolution of the simulation. And then you cannot do much with these. You have to first refine it into the physical properties of interest out of possibly hundreds, and the structure that you're interested in this case, galaxies. So you can see here at the top, you have galaxies in the gas component and the same galaxies in the stellar component, but this is only an example of a couple of hundred compared to the millions that actually live in these simulation boxes. Then you can further zoom into one object and look at the detailed structure in each component. So you can see how hierarchical this data is. You have to move back and forth between the holistic view of the simulation and the individual view of the properties of the individual objects that you're interested in order to build a picture of your science case. So the problem, to summarize, is that these simulations require very large investments. I'm sure this is not only the case for state-of-the-art cosmological simulations, but also any kind of simulation that is used in science at the moment. They require years of development, hundreds of millions of CPU hours, and petabytes of storage. This is an example of the largest supercomputer that we have in Europe at the moment. These simulations are difficult to access, explore, and analyze. And this is incompatible with the fair data principles. And it's going to become an even greater challenge for the next generation of exascale simulations. Obviously, our capacity to process this information does not scale with the growth of the simulations. You can see here in this image imagined by AI, not even with a scientific sweatshirt full of hardworking students, hundreds and hundreds of them, it will be impossible to even scratch the surface of the information contained in these data sets. So we definitely need machine learning to exploit this kind of large data sets. And like I said before, don't think of just simulations. This is intended to be more general. So how can we approach this challenge using machine learning? The ideal tool for this should have certain requirements first. It should build a representation of all the structures in the simulation, in this case, the galaxies in this example, without the costly need for humans to generate labels for these objects. It should also allow exploration of the entire simulation using an interactive visualization. And it should enable inspection and analysis of data sets that grow to arbitrarily large sizes. And lastly, it should be code agnostic, meaning that the simulation analysis and exploration tool should not care what specific code was used to run that specific simulation. This is an example of a problem that we actually have now, that specific analysis tools are built by the same people that develop the codes specifically for those codes. And this is where the power of generative deep learning really shines. So we can go back to this quote by Richard Feynman, where we can use generative deep learning as a set of tools that can take all this complex information from the simulations and synthesize it. And by recreating it, this is how they work. They understand how the data is generated, and by doing that, they understand the structure of the data and are able to synthesize it very effectively so that they can help us understand it. So it's another layer on top of the simulations. Or it's a layer that can also be applied on top of the observational data if it has a similar structure. These kind of tools are designed to learn the underlying distribution of a data set just from a lot of samples without the need for costly labels. So they're self-supervised or unsupervised models. And then they can project the high dimensional complex data onto a very low dimensional representation that is a great way to explore and interpret it. And you can imagine this in this way, assuming that the data lives in a very high dimensional, very complex space, but it's very regular. You can imagine squeezing all the space out of this three-dimensional space and unfolding this data onto a two-dimensional intrinsic space where you can actually visualize and explore it more effectively. And they do this by taking the data itself. In this case, we have an example of the structure of a galaxy in one of the illustrious TNG simulations. You put it through a generative deep learning model. In this case, this is a variational autoencoder that puts the information through a bottleneck and tries to reconstruct it on the other side. But this bottleneck only allows a little bit of information to go through. So it has to prioritize the most important aspects of your data. And in that sense, it can compress the structure into only a few numbers. And this is what makes the space more intuitive and more easy to explore. So we're developing these two tools called the Spherinator and Hipster, which together allow you to take the data, the raw data from the simulations without all this manual processing on the right side. You go straight from the raw snapshot data. Then they allow the user to select the object of interest. In this example, it's galaxies, and also the physical properties. For example, mock images or even 3D structures of the objects. They put it through a generative deep learning model. It does not have to be necessarily the one shown here. We have some flexibility to include your own models. And this model builds this representation that can be projected on a sphere that can be visualized interactively. And here you can actually see all the images of 50,000 galaxies in this simulation, which is the entire data set. They're all contained here in this hierarchical representation, and they're arranged or classified sort of in this similarity space, where around the point you find galaxies that have similar structures. So it provides a very powerful way to explore your data set. It also shows you how the model understood the data. So you can generate arbitrarily large numbers of extra data points, in this case, images. And it lets you explore the individual properties of objects through this sort of overlaid catalog that you can see here, where you see all the metadata on a specific galaxy. In this case, you can go back to the simulation database and pull out, for example, the formation history of the galaxy with all the progenitors and some other aspects of the data. It also lets you create catalogs in the similarity space and download them to your local machine, and also to select data in arbitrary regions based on similarity, and then download this data to your laptop for local analysis without having to download the entire data sets. Here's a little demo of the tool in action. This is a web demo that we actually have online that you can play around already with. So you have this historical representation of the model that was learned from all the illustrious TNG galaxies. Then you can overlay the actual data that was used to train the model. And because it's a hierarchical representation, when you zoom in, it's like Google Maps. It shows you more and more details. And in this case, it shows you more and more of the data in the data set, so that it can show you 50,000 images or millions possibly in the exascale era. You can scale it indefinitely. Then you can point and click on one of these objects that you're interested in and get all the metadata, and then get the images, for example. Here's another demo of a tool that we're developing here at HITS with one of our students. We're working on not just visualizing the images, which is what astronomers usually do with galaxies, because this is how we see galaxies in the sky. In the simulation, we actually have the full 3D representation. So as you can see here, you can select the field of interest, the dark matter halo, for example, or the galaxy itself, and visualize it in 3D in real time, and you can rotate the views of the object. And just as an example of what you can do with these kind of tools in terms of actual science, we've been working on this project to sort of update the way that we think about galaxies. Historically, we have been describing galaxies using single numbers based on our intuition about what's important, for example, how bright they are, their size and their shape. But we know, and this is also motivated by this 100-year-old classification of galaxies based on what they look like. But this is a very simplified description. Galaxies are definitely not points, and they're not described with only a couple of numbers. If you go out to data from the modern observatories like Hubble and James Webb, you can see that galaxies are actually much more complex and diverse objects. And you can imagine that it would be very difficult to describe these images using a couple of numbers or simple shapes like in the Hubble fork. So, and these galaxies are very complex objects that emerge from a combination of many physical processes. And we want to understand what these processes are based on the structure of the galaxy. So to do that, we can actually ask the machine directly how many numbers are needed to describe the structure of a galaxy, just by training it on lots and lots of images of galaxies, of real galaxies or simulated objects. And we already have some interesting results on this. We're looking at this representation of galaxies in 3D that you can see here. And we're asking, instead of condensing this to a number, how can we compare these two 3D distribution directly? How different are these two objects in a non-parametric way? And we've looked at how much information is contained in some measures of distance this way. And we find that the shape of this dark matter halo that these galaxies form in actually contains information about the eventual formation of the galaxy and its luminosity. So this is something that potentially can lead to predictions from the simulations that can be sort of contrasted with the actual data. to do some scientific discoveries. We can think of more applications. You can do exploration, so you can explore correlations between all the physical properties of the structures. You can interpret the correlations that you see using the labels that you already have. So in this example, it would be, for example, the morphology of the galaxies or the environment of these galaxies. You can also use it to do model selection, to compare the detailed structures of the objects non-parametrically, and to do this for entire distributions of millions of objects, both in the simulations and in the observational data. So in this way, you can compare apples to apples, the predictions of your model, which is the simulation, and the observational data, which comes from like this very large surveys that are going on at the moment. And here I want to stress that if you work with very large simulations or even observational or experimental data sets with a lot of complex structures and high dimensional feature spaces, then you should definitely come talk to us, and maybe we can help you use our tool to better understand your data. And just to summarize, we've trained the first prototype on 50,000 synthetic images from the illustrious TNG simulations. We also trained it on 150,000 real images from Galaxy Zoo. And we find that it effectively learned dissimilarity space based on color, morphology, inclination, and galaxy interactions. And we're now working on extending this beyond 2D images to full 3D structures or even beyond. These 3D structures can be described most effectively using geometric deep learning. And like I showed you, we're working on exploration tools to visualize these 3D structures. We're also implementing an agnostic data preprocessing workflow where you can intuitively select and fetch data from any simulation without any specific expertise. And to conclude, here's the information on the demo. You can already scan this QR code and play with it even in your phone. It's pretty lightweight. We've submitted this for publication. The code is publicly available, and I invite you to help us develop it. And if we can help you explore and interpret your simulations, I'll be very happy to hear from you. And here's my email. So I already told you basically why we're doing this, why simulations are difficult to interpret, and how we can use generative deep learning to understand them better. And now I'll leave the floor to Bernd Dozer, who is also working here with us at HITS, and he's responsible for most of the software development aspect of these tools. He will tell you how to use them and how to develop them for your own needs. Thank you.
So thanks again for giving us the opportunity to present our work in the space webinar. My name is Bernd Dozer, and my scientific background is computational chemistry. However, I have worked for almost 15 years now as a scientific software engineer in many different fields. My main focus is HPC and machine learning using C++, CUDA, Python, and many other things. As Sebastian said, he has presented the scientific background and potential applications, and I will focus more on the technical design and the implementation. So first, I will say a few general words about the best practice development environment setup. Then I will introduce our spherinator machine learning model and explain its training process a little bit. Afterward, I will explain our workflow, Hipster, which is used for inferences to display the modeled galaxies and the dataset projections. But let me start with a few words about best practice software design. We respect to the design and implementation, we follow the so-called FAIR principles that have been established in the scientific community. But what are these principles and why are they important? These principles state that the software should be easily findable and accessible, interact with other software through open standards, and be simple to use and modify. You can find a very good overview here in the given reference for more details. Before diving deeper into our model, a few words on useful frameworks and technical environments. The slides contain links to the different tools. We have established a development environment at GitHub that covers the entire software lifecycle. This means from feature design up to the deployment. And we use GitHub Actions for providing continuous integration. This contains static code analysis and test section and so on. For the dependency management, we use Poetry, and DependerBot from GitHub is used for automated version and security updates. The trained models will be converted into a ONNX open standard from Microsoft. And this enables interoperability among machine learning frameworks and programming language. So you can easily use the model on different architectures with different frameworks and very different languages from C++, Rust, Python, and so on. And use weights and biases to track and orchestrate the training process. This development setup complies with the FAIR principles, providing stability and allowing for the necessary flexibility to make steady improvements to our software. So, but now what is spherinator? The term spherinator is derived from the spherical latent space manifold. So let me now explain this a little bit more in detail. The spherinator machine learning model is built on a dimensionality reduction. This allows to learn data features automatically. To achieve this, we use a generative model known as convolutional variational autoencoder. This is an unsupervised machine learning approach that enables us to generate new data by identifying patterns in existing data. Unlike a plain autoencoder, which reconstructs images from a single point in the latent space, the variational autoencoder uses a sample from a learned distribution. And as a result, the neighborhood in the latent space represents similar features. Although the rotational invariance is very crucial for learning features from galaxy images. They should not depend on image rotation. To achieve this, the image with the lowest reconstruction loss is selected, and only this image is then used in the training step. It is possible to have also other manifolds in the S latent space, but the spherical manifold is the most suitable for visualization. You will see this. The power spherical distribution was published 2020, and this provides a reliable method to handle this spherical latent space. We have here the direction, and this represents the position in the latent space. And kappa is a measurement for the distribution width, like the variance in a Gaussian distribution. And you can choose different dimensions from a circle, which has a dimension 2. We use a sphere with a dimension 3, but you can go up to every hypersphere by choosing a dimension greater than 3. And here you see in this picture different directions, 3 different directions with also 3 different concentrations kappa. And the distribution width is really broad for small kappas, and for larger kappas, the width of the distribution is narrow. The loss function is one of the most critical aspects of the model training. It consists of the reconstruction loss and the Kullback-Leibler divergence. The reconstruction loss is calculated pixel-wise over the Euclidean distance, pixel by pixel. And the Kullback-Leibler divergence is a measurement for the difference between 2 distributions, between the power spherical distribution and a reference distribution function. In the typical Euclidean space, the reference function is a centric Gaussian distribution, but we use, in the spherical case, we use a uniform distribution. And it is very crucial to find a right balance between these two parts of the loss function. To achieve this, we use the lambda factor to scale down the Kullback-Leibniz divergence. Now to the training. We use PyTorch Lightning for the training. This is a built-up framework built on PyTorch itself, and it decouples the research code from the engineering code. This has several advantages. It is easier to read. It is way better to reproduce, and you can easily scale up to by using accelerators or distributed hardware. By using the command line interface from PyTorch Lightning, you can everything define in a single file what is needed for a training setup, for a training process. You see this config YAML file here. You have to define the model, and this is simply the class path to your Python code where the model is defined, and the arguments of this class. And it is also possible to use further models in the arguments. For example, for the encoder and decoder, here you can easily integrate existing models, for example, a ResNet encoder or a visual transformer encoder, and put it in this line. The second part is the data part. Here you have to define your PyTorch Lightning data module. And you can, at the moment we are using 2D images. You can easily put your own images in a data directory, put it here, and set the correct extension. It can also be a JPEG or something like this. And then you can use the spherinator with your own images. And also all the other things are defined here. You see the optimizer, the learning rate scheduler, and the best feature in my eyes is the trainer section. Here you define the accelerator. So you can easily switch between the normal CPU usage and by typing here GPU, you can use your built-in GPU accelerator with the number of devices. So if you have 4 GPU cards in your machine, you can here use all 4 cards for the training. So it's very, very easy to scale up. And also in the trainer section, all the other things like the logger, where we use weights and biases, or some callbacks for storing the best models to store reconstructed images. All things are defined here, and you can simply start your training by calling the spherinator with this config file. And examples of config files are also located in our GitHub project. Okay, then we come to the monitoring. The monitoring is another key aspect for the training. And I think weights and biases is a very comfortable way to track these experiments. you have all data in one platform, and you can simply share the data with your colleagues. You can store the trained models, can organize it, you have version control over it in a model registry, and can then use it for fine-tuning, staging, or production. So this means you have not to search for the right model and copy it from machine to machine. You can simply load it from Weizenbeises. And you can also optimize the hyperparameters, which is really cool. And it's absolutely free for academic research, this tool. Okay, so then we come to the inference. Here we have implemented the Hipster, and Hipster is a workflow which is needed for the visualization, to visualize our model and the projections. We need to visualize the generated images from the latent space with a trained model. And here we use the hierarchical progressive survey called HIPS, the HIPS format. And this opens an ideal way to visualize the spherical manifold in a hierarchically way. This means, as you saw it by Sebastian, that you can zoom in and get more and more generated images in this region. So we have only to generate this HIPS file structure, and then we can use a program, for example, Alien Light, to make the final visualization. And to build up these all the information, here a short overview, schematically overview over the HIPS workflow is shown with individual tasks. To generate the HIPS tiles, we call the decoder for all hierarchical points of the spherical latent space. And the encoder part of the model generates a catalog file, and this contains the location of the latent space for a given data set. And all the other tasks produce images and tables which are needed, which is needed for LED Light to provide the necessary information. So with that, I would like to summarize. The take-home message is Spherinator and Hipster provide a promising solution for classifying large data sets in general. A key for establishing a stable technical framework is to obey modern software development techniques and following best practices such as the FAIR principles. This allows continuously improving our project. Currently, we evaluating new encoder and decoder models and loss functions to further improve our reconstructions and reflect more image details. In addition, we assessing appropriate workflow frameworks to establish and expand our Hipster workflow. And we are going to test geometric deep learning that would provide a direct way to train 3D structures with rotational invariants. Finally, as mentioned by Sebastian, you can find the prototype and the source code at GitHub. If you have any questions, please don't hesitate to contact us. Sebastian can assist with scientific inquiries, and I can help with technical and general inquiries regarding modern software development and machine learning. Thank you for your attention.